Did you know that modern aircraft don't rely on human reflexes alone to stay stable in the air? Instead, they use advanced control systems that automatically adjust to different speeds, altitudes, and flight conditions. But how does an aircraft fine-tune its control settings mid-flight? The answer lies in Adaptive PID Controllers. Stay with me till the end of this video as we break down how an aircraft dynamically adjusts its PID controller tuning using adaptive control techniques to ensure smooth and safe flights. Every modern aircraft is controlled by Flight Control Systems, FCS, which include PID controllers to regulate flight parameters like pitch, roll, yaw, and altitude. A PID, proportional integral derivative controller, continuously calculates the error between the desired flight condition and actual aircraft behavior, and then adjusts control surfaces like ailerons, elevators, and rudders accordingly. But here's the problem. Fixed PID gains, reset time, and rate time don't work well across different speeds and altitudes. The same controller settings that work during takeoff may cause instability at high altitudes. So, how do we fix this? By applying adaptive PID tuning. Imagine an aircraft taking off at low speeds, where more aggressive control is needed to counteract turbulence. Now compare that to cruising at high altitudes, where the aircraft needs smoother, more stable responses. If PID parameters remain fixed, the controller might become too slow or too aggressive, leading to oscillations or sluggish control. To solve this, we use adaptive PID controllers, which automatically adjust their tuning parameters in real time. Now, what is adaptive PID controllers we have been talking? An adaptive PID controller is a type of PID controller that automatically adjusts its tuning parameters P, I, and D settings in real time based on system changes or external disturbances. Unlike traditional PID controllers, which have fixed gains, adaptive PID controllers modify their behavior dynamically to maintain optimal control performance. Sounds interesting? Yes, it is. Most of the standard PID controllers we have seen in industrial environments work well for systems with fixed dynamics, but real-world systems often have variable dynamics or unknown dynamics due to varying operating conditions, load variations, nonlinearities, and aging of components. An adaptive PID controller is the key here and tunes itself to handle these variations effectively. Adaptive PID controllers continuously modify their P, I, and D gains based on real-time flight conditions. Let's explore some key adaptive techniques used in aircraft control. 1. Gain scheduling. The aircraft control system stores predefined PID gains in a lookup table for different flight conditions. Sensors monitoring parameters like airspeed, altitude, and MAC number enable the adaptive PID controller to automatically switch to the appropriate PID gains based on lookup tables of these sensors, which sense affecting conditions. For example, during low-speed takeoff, it sets a higher P gain, based on control input sensors like airspeed and altitude. During high-speed cruise, it sets a lower P gain and higher D gain to avoid overcorrection and oscillations, again based on control input sensors like airspeed and altitude. The aircraft switches between these settings using sensors that monitor speed, altitude, and Mach number. 2. Model Reference Adaptive Control, MRAC. The system continuously compares actual flight behavior with a reference design model and fine-tunes PID gains to match the desired performance. If differences occur due to altitude or speed changes, the PID parameters are adjusted in real time to reduce error. It is used in fly-by-wire systems in modern aircraft. See, this is not a fixed format. It can take any settings based on current behavior. 3. Self-tuning PID using online parameter estimation. The controller continuously identifies system dynamics using real-time data, such as pitch rate and angle of attack, or machine learning techniques to adjust PID parameters accordingly. It helps during turbulence, gusty winds, or sudden weight shifts. 4. Neural networks and fuzzy logic. AI-driven controllers predict and adjust PID gains dynamically for optimal stability. With advancements in AI and machine learning, adaptive PID controllers are getting smarter, making modern aircraft safer, more efficient, and more responsive than ever before. So next time you're on a flight, remember, behind that smooth journey is an intelligent control system, fine-tuning itself in real time to keep you safe in the skies. If you found this video insightful, don't forget to like, subscribe, and hit the bell icon for more exciting aerospace and control system content. Thanks for watching, and see you in the next one.